use this called a hash. So the idea is that like you can compute this function very easily, and you just get some sort of information from it. But if you want to like go backwards and get the original information that you put into the function, it's actually very difficult. So I just like found some hash calculators online. I hashed ABC, and got this as the output. I hashed ABB, got a completely different random string, even though I only changed one letter. And then I went and copy-pasted like the first book of the Bible, and I put it into the hash calculator, and I got the same, like, I mean, it's like basically the same length, maybe even a little shorter, but it's still completely random. So if I was to take any one of these and like beam it back, well, that would be very impressive because, you know, it's just a bunch of random letters. And also the cool thing about hash functions is that it's, because, you know, you're taking like a full length thing, it can be any length, and you're setting it to a specific length, so that means like the part of the function that you can use as an input is way bigger than the part of the function that you get as an output. So certain inputs are all going to take you to the exact same output. You understand? Like if you have like, I mean, you have 50 pigeons and only 2 pigeonholes, you're trying to throw all the pigeons in holes, there are going to be multiple pigeons in each hole. And that's like basically for sure. At least one of the holes is going to have more than one pigeon. And so that's sort of what's happening with this hash function. But what's cool about it is that you can't really predict which holes are going to have which pigeons. So like the same thing, like if you only change a small thing about the hash input, you get a completely different output that you can't really find any relationship between the two. And so this is just like an example of a sort of function that's easy to do in one way, but hard to do in the reverse. Oh, I don't know why it's a different color. But okay, we're gonna tell you about circuits. So if you've heard about like electrical stuff, you know, you probably know what a circuit is, but this is kind of different. So we're gonna talk about the two kinds. There's Boolean circuits and arithmetic circuits. For this like specific talk, we're going to be mainly focusing on Boolean circuits. But the idea is that if you take an arithmetic circuit, you can actually turn it into a Boolean circuit. And the only difference between the two is that Boolean circuits use only like and or, the logical functions. And arithmetic circuits can do multiplication and addition. So the Boolean circuit is sort of like a more specific version of like an arithmetic circuit. Yeah, so one thing that might be like surprising to you is that any polynomial can be written as a circuit. And so because you can basically take many like different types of functions and turn them into polynomials using like, what's it called? Like Taylor series. So you can just sort of take a function, turn it into a polynomial, take the polynomial, turn it into an arithmetic circuit, and then take the arithmetic circuit and turn it into a Boolean circuit. So you get that almost any sort of function can be written as a Boolean circuit. Let's just draw one of these out because I get that like the idea is probably pretty weird to understand. So like say we want to say, we just want to compute if 2 people have the same input. So we've got this and here, and then we've got 2 little wires that go into the AND that represent the inputs. And we've got 2 little, or no, we only have 1 output, and that's like the evaluation of the circuit. So this can be a 0 or a 1, a true or a false, and this can also be a true or a false. So say, yeah, basically then the output, if you have like 0, 0, so these are like your options. You want to compute AND. You just go, okay, so this person said no, this person said yes. If we want to see if they agree, and if they both say yes, then the answer is no. They did not both say yes. Both said no, once again it's no. But they both said yes, so that's true, and they didn't agree. So this would be the possible outputs for like this specific circuit. But you can make bigger ones. So like, say you want to check, you've got 2 inputs, like per person. It's like a 2-digit number. You know, you have 1, 0, and like 0, 1. And you want to see, well, there are like different things that you could see. If you just want to compute like and, or, and. So you see this is false, and this is true. And then you want to see whether these both things are true, and they're not, so the output is false. This is just like some examples of what like Boolean circuits can be.
So how would you do addition?
Okay, so addition of like a single bit is not too difficult. You know, you just do an OR. So you have like 0, 1, 0, 1. If both the inputs are 0, you get 0. Both the outputs are 1. Oh, I guess not. It's just not just OR, because you have to actually carry things. So you could have a potential of 2 outputs, where you end up getting, you know, because your output would have to be 1, 0 for binary addition. So I'm not actually sure, but yeah, you can probably look it up or something like that. But it would have to be a bit larger of a circuit.
So I would just make all numbers into the binary and do this and make polynomials?
Yeah.
Why did you need Taylor series for polynomials?
If say your say your function is like sine, cosine.
That's not good.
Something like that. If you've got like the sort of function that doesn't immediately become a polynomial,
Oh, okay.
and you want to estimate it with a polynomial to any like specific degree of accuracy. Okay, so now we actually have everything we need to know to talk about what a garbled circuit is. So this is a way to encrypt the circuits so that you don't, like each individual person takes their input and they put it into the circuit, but they don't have to say anything out loud. And the only thing anyone actually gets from the evaluation of the circuit is the output that they would have learned anyway, if they just had like a black box where they throw their inputs in and then it throws out the output. So it's made possible using these things, the symmetric key encryption, where everyone already has the key in mind, and they can encrypt something, and then throw it out, and nobody else who wasn't involved will be able to understand it, and then the other person gets it, and they can decrypt it because they already know the key. It also involves key transfer, so they need to be able to decide on that secret key. Oblivious transfer, I can see why it's kind of weird. You don't know why you need this, but you do. And one-way functions, once again, it's the sort of thing that makes stuff like key transfer possible. Yeah, so the idea is that basically we have the 2 people again, Ginny and Evan. So Ginny's job is like to generate the circuit, or to garble the circuit, which basically means to encrypt it. So Ginny already knows what her inputs are going to be to the function. So she takes her inputs and she already incorporates them into whatever the circuit is going to be, and does some sort of encryption on it. Evan receives this encrypted circuit and is able to use his inputs to actually evaluate the circuit without learning any information about what Ginny put as her input.